This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss the solutions, relevant concepts, and the scoring guidelines associated with some of the parts of our 2020 mock AP Calculus exam, Form AB, Question 1. My name is Steve Kokoska. I'm a professor at Bloomsburg University of Pennsylvania, and I'm a former AP Calculus chief reader. Form AB Question 1 involves a continuous function f with domain -2 less than or equal to x less than or equal to 9. The graph of f is given, and it consists of 3 line segments with 2 quarter circles. A new function g is defined as g of x is the definite integral from 0 to x of f of t dt for x between -2 and 9. In Part I, the student is asked to find a limit. And there's that phrase again, show the computations that lead to your answer. We really want to see some good communication skills. In order to solve this problem, we'll need to use Lhopitals Rule. Now, I won't read through this entire statement. It basically says that if we have a limit in an indeterminate form of type 0 over 0 or infinity over infinity, then we can find the limit of this quotient by taking the limit of the quotient of derivatives. As an aside, this concept has been tested pretty regularly since its reintroduction into the AP Calculus curriculum. And to earn full credit, good communication is extremely important when using this rule. Before we solve this problem, let's take a closer look at Lhopitals Rule. In words, Lhopitals Rule says that the limit of a quotient of functions is equal to the limit of the quotient of their derivatives, provided, of course, that the given conditions are met. It's very important to verify that the original limit is in an indeterminate form of type 0 over 0 or infinity over infinity. You can't just arbitrarily apply this rule to any limit of a quotient. Lhopitals Rule is also valid for one-sided limits and for limits at infinity or negative infinity. Well, again, provided that the conditions are met, that the limit, the original limit, is in one of the indeterminate forms. This is a pretty amazing technique, and a proof of a special case of this rule is usually presented in AP Calculus texts. And there's a very nice visualization of this special case using technology, available in a calculator application on the TI website. Lhopitals Rule can be used repeatedly. That is, after applying the rule once, the limit may still be in an indeterminate form. And we can use Lhopitals Rule again and again if necessary. And finally, there are other indeterminate forms associated with limits, but these are not tested on the AP Calculus exam. But I think most college calculus courses cover these forms. The basic approach to solve a limit involving one of these other forms is to rewrite the expression so that it is in an indeterminate form of type 0 over 0 or infinity over infinity. And then we can apply Lhopitals Rule. To solve this limit, the first thing we'll do is examine the limit of the numerator and the denominator separately. To find the limit of the numerator, I can split this into 2 separate limits. Each of these functions is continuous, so the limit here is 3 times 0 plus g of 0. But g of 0 is by definition this definite integral, which is 0. So the limit of the numerator is 0. The limit of the denominator is the limit as x goes to 0 of sine of x, which is sine of 0, which is also 0. So the original limit is indeed in an indeterminate form of type 0 over 0, and we can use Lhopitals Rule. Now let's use Lhopitals Rule. Take the derivative of the numerator and the derivative of the denominator. In the numerator, the derivative of a sum is the sum of the derivatives. And the best I can do at this point is to simply write the derivative of g of x as g prime of x. In the denominator, the derivative of sine x is cosine x. The resulting expression is no longer in an indeterminate form, so we can evaluate this limit. In the numerator, first use the fact that g prime of x is equal to f of x. Then the limit is 3 plus f of 0, and f of 0 is found from the graph. In the denominator, the limit is cosine of 0, which is 1. So the final answer here is 1. Here are some typical scoring guidelines for this type of problem. This type of limit question is typically worth 3 points. The first point is for verifying the conditions necessary to apply Lhopitals Rule. That is, verifying that this limit is in the indeterminate form of type 0 over 0. The second point is for evidence of applying Lhopitals Rule, that the student has attempted to take the derivative of the numerator and the derivative of the denominator in the context of the limit problem. And the third point is for the final answer. And remember that a final numerical answer does not need to be simplified. Here are some interpretations of these guidelines to help award points and to prepare for problems like this on the next AP Calculus exam. The first point is earned for verifying that both the numerator and the denominator approach 0. In general, the student does not need to reference continuity or differentiability to evaluate either of these limits. That would be nice, but usually it's not necessary to earn the point. In the past few years, any notation that includes equals 0 over 0 does not earn the first point. And this equality can appear in disguise, and that means in an unsimplified expression with an equal sign. However, other expressions that are acceptable ways to indicate an indeterminate form include an arrow and then the fraction 0 over 0, or even the phrase equals indeterminate form 0 over 0. The second point in this problem is earned for presenting a limit of a fraction with numerator and denominator that are clear attempts at derivatives. Now, there's certainly some professional judgment here in awarding this point. The second point can be earned without proper limit notation, but the total response, must in some way convey a limit. And again, we generally use some professional judgment. And finally, the third point is earned for the correct answer, 1. In Part J of our free response question, a new function h is defined, and we need to find h prime of the square root of 2. There are two important concepts necessary here in order to solve this problem. We'll certainly need to use the product rule, which says that the derivative of f times g is f prime of x times g of x plus f of x times g prime of x. This is one of the basic differentiation rules taught in every first-year calculus class. And we'll also need the chain rule. This tells us how to find the derivative of a composite function capital F of x equal to f of g of x. And to find capital F prime of x, we start at the outside taking derivatives and work our way inside. So that capital F prime of x is equal to little f prime of g of x times g prime of x. The chain rule is a pretty important concept, so let's take a closer look at this idea. In words, this says the derivative of the composition of two functions is the product of the derivative of the outer function evaluated at the inner function and of the derivative of the inner function. Here is some other common notation to illustrate this rule. We often use an open circle to represent the composition of the functions f and g. And here, just another common way to indicate the derivative. This last item is a step-by-step procedure for applying the chain rule. I find this is helpful for students when they first learn this rule. The most important part, and perhaps the most difficult thing before applying the chain rule, is to correctly identify the outer and the inner functions, f of x and g of x. And this takes practice. Then find f prime of x and g prime of x separately. And then finally, put everything together and write the derivative of the composite function as f prime of g of x times g prime of x. All right, let's use these concepts and start by finding h prime of x in general. Use the product rule and the chain rule. And then remember that g prime equals f. Now, use this general expression to evaluate h prime of the square root of 2. G of 2 we found in another part of this free response question. It's pi minus 4. And f of 2 is read from the graph, given in the statement of this question. A little simplification, and the final answer is pi minus 4. Note again that students do not need to simplify a final numerical answer. This problem was worth 3 points. 1 point for correct use of the product rule, 1 point for correct use of the chain rule, and 1 point for the final answer. Here are a few interpretations of these scoring guidelines. The first point is earned for an expression in this form, where a and b are non-zero constants. We believe that an expression like this demonstrates conceptual understanding of the product rule. Similarly, the second point is earned for this expression as part of one of the terms in the student's expression for h prime of x. This demonstrates conceptual understanding of the chain rule. The third point is earned for the correct answer with supporting work. So that means a bald answer here earns no points. Now, some students don't communicate much in solving a problem like this. So we often draw this sort of line in the sand. This is the minimal computations that are necessary to show to earn all 3 points in this problem. Now look, we'd really like to see more, but this conveys just enough understanding of the product rule and the chain rule, and it includes the final answer. A gentle reminder that the student must evaluate g and g prime to earn the third point. So what I mean by that is leaving the final answer with a g of 2 and or a g prime of 2 or f of 2, that's not considered a final numerical answer. And finally, as in many problems, there is an eligibility criteria here for the third point. And that is that the student must earn the first 2 points to be eligible to earn the third. I hope this video gives you a good idea of how to solve these problems using the necessary AP Calculus concepts, and a reasonable expectation of how they would be scored. And this video concludes AB free response question number 1.